Morning, everyone. We're still waiting for one virtual committee member, and I have one physical committee member / research advisor behind me. And you can all feel free, if you want, to turn on your video so that I can see your inquisitive faces while I give the talk. Hi, Professor Mehta.
You might regret asking that, but.
Hi, Tim, how are you?
Very good. Excited to share my research with everyone.
Tim, just to let you know, if your voice does get cut off, I will turn off my video so that I can hear you clearly.
Okay, sounds good.
Okay, because that has known to happen a lot of times.
Okay.
Right.
I'm hoping that being hardwired on the campus network and internet,
you would be surprised internet dropped off in my class.
Of course.
So
Murphy's Law includes a coefficient for global pandemics.
absolutely.
Tim briefly explained that you missed that your attachment did not get added on to your emails.
I omitted a document that I was supposed to send out to you committee members and also to Tom, the department head. It's a thesis defense request form. I had been communicating with everyone. I left this form off. And so if it's okay with you guys, I'd like to retroactively put in last week's date and send this out to have you guys sign and date it as well.
Fine with me.
Cool.
Fine with me too.
I'm going to close your door real quick so I don't get too.
Hi, Dinesh, Shubham, Mark. Hi, everyone. This is Christian with a little C on the screen.
I thought that might be you.
Okay. And so if everyone's ready, I can get started. Okay, so welcome everyone to my virtual thesis defense. My thesis is titled Universal Observable Chemical Bond Analysis, Gradient Bundle Decomposition of the Electron Charge Density. So without further ado, I'll just jump into things. So in modern computational chemistry and material science, we're computing more accurate energies, wave functions, charge densities more efficiently for larger and larger systems. But these energies that we're getting more accurate at calculating are system energies. Although the phenomena that we're generally interested in are local phenomena that are associated with local energies. In chemistry, this takes the form of chemical reactions with forming and breaking of bonds. We have functionality, radical sites. In material science, they're interested in grain boundaries, crack tips, dislocation cores, all local phenomena that have local energies ascribed to them. Now, density functional theory tells us that all the information about a system's energy and related properties should be contained in the charge density. And so a natural approach to get at local energies is some form of charge density partitioning. But there's a problem in that kinetic energy is ambiguous over an arbitrary region of charge density. And what we're interested in our group is this ongoing process of accessing these local energies. One approach to a charge density partitioning is a topological partitioning. They call this the quantum theory of atoms and molecules. It was introduced and developed out by Richard Bader in the 60s, and it's been extended since then. When you do a topological partitioning, you get a set of unique regions that correspond to atoms and bonds in some system. And these regions satisfy a boundary condition of zero flux of the gradient of charge density. And this, in fact, gives them a well-defined regional kinetic energy, overcoming the problem of ambiguity of kinetic energy. And they also obey the virial theorem, which in an equilibrium system equates the total energy to the potential energy to the kinetic energy. So just by knowing the kinetic or potential energy of the system, you can also know the total energy of that system. A further extension of a charge density partitioning using zero flux surfaces is what we call a gradient bundle decomposition. This is an infinitesimal partitioning of a system into differential gradient bundles. When you do this, you condense the charge density into a two-dimensional, well-defined energy space. And doing this enables the direct inspection of the local energy distribution to the maximum resolution that you're capable of doing under the laws of quantum mechanics. So today I'm going to go over some quick background. I'm going to review what a topological partitioning is. We're going to look at why local kinetic energy is ambiguous over an arbitrary region. And then we're going to go over the concept of what a gradient bundle decomposition or an infinitesimal zero flux surface partitioning is. And then I'm going to introduce the novel algorithm that I developed as the majority of my PhD work, which is necessary in order to actually perform a gradient bundle decomposition of a system. And this algorithm has two main parts of topological feature extraction from the charge density, and then the actual gradient bundle decomposition. Doing so gives us the differential gradient bundle condensed charge density, and I'm going to show that this naturally leads to a redefinition of these unique chemical bonding regions that we call bond bundles. I'm going to show that we can use the ability to inspect a local energy distribution to come up with a rationale for the preferred crystal structure of pure metals. And I'm also going to show that we can observe dynamic energy distributions during changing events like bond breaking and formation. And then I'll wrap everything up. So let's get started with the background information. First, we'll go over a topological partitioning. As an example, I'm going to use ethene. And to make things super simple, let's take a two-dimensional example by cutting through the molecular plane and mapping some contours of charge density on this plane. We can then use our spare dimension to extrude out the charge density as a height variable. And when we do so, the topology becomes much more apparent. And so we have critical points in the charge density. We have peaks that we call nuclear critical points. And we have saddles that we call bond critical points. There's also paths through the charge density. And these are gradient paths in that they simply walk in the uphill or downhill direction, starting at some point. The unique gradient paths start with bond paths, and these are ridges connecting bond critical points to nuclear critical points. There's also some unique valley paths. One of them is the downhill path from a bond critical point. And there's a second type of valley path that goes downhill from a nuclear critical point. And these blue valley paths are the steepest descent paths downhill from a nuclear critical point. When you have all these paths in this two-dimensional example, they naturally partition off the system into unique areas. The first area would correspond to an atom. So this is a nuclear critical point and all of the hillsides around it. The second region we call a bond bundle. It's this chemical bonding region that's defined by the steepest descent paths from a nuclear critical point. But these bond bundles and these atomic regions called atomic basins, these are actually three-dimensional features. And we can use this same example to get at the three-dimensional surfaces of these regions by taking some other plane, identifying the unique paths in that plane. And then we can see how, in this case, the bond bundle surfaces are defined according to these unique gradient paths. And this gives us, in this case, the double carbon-carbon bond bundle. And I said that local kinetic energy was ambiguous over an arbitrary region. And we can see why that is very simply. So the total energy of some region omega is the sum of kinetic and potential energy. The kinetic energy is generally represented in one of two forms. There's the gradient kinetic energy, Tg, which goes as the inner product of the first spatial derivative of the wave function. It's a gradient with itself. And you integrate this over the entire region. The Laplacian form, TL, goes as the Laplacian of the wave function, which is the second spatial derivative, again integrated over the whole region. Now, in general, these two representations of kinetic energy differ for some arbitrary region, and they differ according to the flux of the gradient of charge density through the region's bounding surface. So if you have the gradient, nabla rho, the inner product of that with a normal vector that's normal to the surface at each point r, this gives you the difference between the Laplacian and gradient forms. That being the case, if we could construct a surface where the gradient is always perpendicular to the normal vector of the surface, so that the gradient lies tangent to the surface everywhere, then this difference goes to 0, and now we have a well-defined kinetic energy over such a region. We call these regions gradient bundles, and the set of gradient bundles includes atomic basins, as well as the bond bundle region. And again, these regions have well-defined regional energies. And so this is a big step in getting at a local energy. So if you have a system of 1,000 atoms, now you can look at 1,000 local sub-energies of this system that will sum to give you the total system energy. But we can construct zero flux surfaces arbitrarily. And in doing so, we can infinitesimally partition the charge density into differential gradient bundles in order to obtain a true local energy distribution. And we call this process gradient bundle decomposition. So here's a quick conceptual example using ethyl alcohol. In any system, the charge density about a nuclear critical point is radial, if you're sufficiently close to the nuclear critical point. So you can simply stick a triangulated sphere mesh within the radial region about a nuclear critical point and seed gradient paths along the nodes and edges of the sphere mesh. Each pair of gradient paths is going to form a zero flux surface segment. And when you do this for all the gradient paths that correspond to a particular element on the mesh, you end up carving out a little volume of charge density that has a well-defined local energy. If you repeat this for the entire system, then you're now doing an infinitesimal partitioning. And this is, of course, a comically large gradient bundle. But doing so requires an algorithmic approach. And this was my principal contribution to the group's efforts. So I'm going to go over some of the steps of the algorithm that I developed during my time here. So for some quick background, we call this tool Bondalizer. And we developed it out of faith that having access to local energies would prove useful in investigating local phenomena. Now, it doesn't seem like it takes a lot of faith to go there, but given the work that was involved, it ended up being a bit of an investment. And this wasn't just faith. This was also based on preliminary success with manual bond bundle analysis, as well as a manual two-dimensional gradient bundle decomposition method that applies to linear systems. Bondalizer is written as an add-on to the TechPlot 360 visualization software, and it's written in shared memory C++ in parallel, and it leans heavily on the GNU Scientific Library, on the Armadillo Numerical Library for number crunching, and on the MeshGen CPP library for the initial generation of the sphere mesh. Work began on Bondalizer in 2004 to simply algorithmically identify bond bundles and related volumes. And we were trying to do this directly based on the topology of the charge density. This work stalled in 2006 because it's a non-trivial problem. I came in 2014, and after around 3 years of working on this topological approach, abandoned it due to the non-generality of that approach. And instead, we switched gears to the gradient bundle decomposition. Now, the algorithm objectives are really simple conceptually. Number one is to guarantee that the gradient bundles are space-filling, so they have to be non-overlapping and fill up all space inside of a system. And this requires the precise identification and inclusion of the topological features of the charge density, things like these bond paths and steepest descent paths. Objective two is to guarantee that the gradient boundaries are bounded by the gradient bundles are bounded by zero flux surfaces. And then as a challenge, these gradient bundles can be highly convex or concave, very small closed surfaces. And so numerical integration, given the shape of these gradient bundles, was also a problem to be overcome. And the makeup of the Bondalyzer code, at this point, it's almost entirely original code by me. But when I started in 2014, I was building off of the work that was done at TechPlot in between 2004 and 2006. And the work towards the topological approach was imperative in my ability to then switch gears to the gradient model analysis approach. So the code may not be in use, but it was not made in vain. So the first step of the gradient model decomposition algorithm is to extract these topological features from the charge density. I'm going to skip over most of these because I didn't do anything new here. I just implemented existing libraries. The first topological feature we need are critical points. And this is obviously required because the gradient model analysis sphere mesh is centered about a nuclear critical point. And finding critical points amounts to iterative Newton-Rassmann root finding algorithms. And I apply a three-dimensional grid method in order to search the system. The next topological feature that we need and we lean heavily on for this algorithm is to be able to construct gradient paths through the charge density. This is important for one because we have to identify bond paths, which are one of the types of gradient paths. And this amounts to a Runge-Kutta algorithm for solving a set of ordinary differential equations. The next thing we need to be able to do is construct zero flux surfaces, which amounts to simply stitching together gradient paths. And then we also need to find ring surfaces. And this is a subset of zero flux surfaces that occurs inside of a ring system, such as benzene or cyclohexane or something. So I am going to talk about the ring surface algorithm because this was a novel algorithm that I had to develop. And it was conceptually a very simple problem that turned out to be less than easy. As an example of how ring surfaces can be a bit tricky, let's take a look at the KSI enzyme. So here's the enzyme at top left. Here's the active site of the enzyme with 4 ring critical points shown in green. And here's a more three-dimensional depiction of what these rings look like. So you see the cyclohexane ring, ring H, is very simple. It's got these straight paths connecting the ring critical point to the nuclear and bond critical points. But the rest of these can just get kind of ridiculous. They're not necessarily planar, and the paths through the ring surface connecting the ring critical point to the bond and nuclear critical points that form the ring aren't necessarily straight lines either. And so to algorithmically get at ring surfaces, we start by simply sort of shotgunning a whole bunch of gradient paths around the ring critical point in the ring plane as defined by the shape of the charge density at the ring critical point. And you can see that in a system like benzene, just this initial generation of critical points or gradient paths essentially recovers the entire ring. But in one of these KSI rings, you might miss a majority of the critical points that make up the ring. And this is the type of system that we're more interested in because this is where everything breaks down. And so in these systems, we have to algorithmically discover the remaining nuclear and bond critical points in the system. And we do this by simply checking pairs of gradient paths for deviation. So we do this based on path separation. If paths reach some threshold gap, then we consider that deviating. Or if the paths are facing away from each other past some threshold angle, then we consider that deviating as well. And then we do this process of sort of walking along the ring surface by seeding additional gradient paths between these pairs. And so in this case, we have 3 missing bond critical points and 2 missing nuclear critical points that have yet to be discovered by the algorithm. And so we just start seeding gradient paths in between deviating pairs. And as we repeat this process, eventually the algorithm just kind of stumbles into a bond critical point. Once we find that bond critical point, we find the minimum length ring critical point, bond critical point path, doing a one-dimensional minimization of path length with respect to where the path has been seeded from. And then we repeat this process, and you can see the algorithm sort of stepping its way towards that next bond critical point. And not all, the shape of the rings can be very dynamic. And so this last bond critical point, you have to get almost right next to it before you can finally terminate a gradient path at that bond. When you do this for the entire ring, this is the set of paths that's recovered. The next step in the algorithm, because we're not just interested in finding the critical points in the ring, we already had those. We're interested in recovering the local shape of the ring surface. And so the next step is to thin and fill the surface paths. And we do this by just looking at the interpath separation gap. And so for for gradient path 1 and some point on path 1 Ri, we check all the points Rj and find the minimum separation gap between point Ri on path 1 and all of the points on the other path. But then we loop over all of the points on path 1 in order to find the maximum minimum distance between any of these 2 points. And in doing so, this gives us just the maximum gap. So for these 2 paths, it would be right here. And then we simply add paths where the gap is too wide, remove paths where this gap is too narrow, and it refines the surface to something like this. The last step is to recover the ring nuclear paths. And this part's fairly simple. We already have multiple paths that leave the ring critical point and terminate at some nuclear critical point. So we find the minimum length existing path and then do a minimization of path length based on where the path is generated from. And so we recover a set of unique gradient paths between the ring critical point and all the other critical points in the ring. And then we also recover the ring surface itself. And these pink segments down here, notice that there's missing gradient paths here. This is where the ring was actually cut off arbitrarily by the boundary of our system. And so my ring surface algorithm still recovers what would be the ring bond critical point path right here. And this is important because you may not have complete data when you're doing a gradient middle decomposition. And so with all the topological features in hand, we can actually perform a gradient middle decomposition. And the main goal here is to make sure that the gradient bundles, again, fill all space and are bounded by zero flux surfaces. And the way that we guarantee that is by how we construct the spherical mesh. Because the spherical mesh defines where the gradient paths are going to be seated. And so that's how we can control whether or not these gradient paths are going to correctly follow topological features like bond paths or ring surfaces. And so taking benzene, one of the carbons in benzene as an example, we generate an initial mesh by subdividing an icosahedron. We represent the mesh as a set of node indices that correspond to an array of node positions. Edges on the mesh are represented as an adjacency list. So edge I is represented by node edge I1, node edge I2. And then we similarly represent triangular elements by adjacency lists as well. The first step in refining our mesh so that it correctly adheres to the topological features of the charge density is to move sphere nodes to where the bond paths in the system intersect the sphere. So if this orange dot is the initial location of the node that was moved, we simply step down the gradient path, or step down the bond path until we find where it intersects the sphere, interpolate the intersection point, and move the node to the intersection point. So that part's very simple. Then we apply what's called jiggle mesh, which relaxes the rest of the mesh, keeping the bond path intersection nodes intact. The more complicated part of the process is to recover the ring surface intersection with the sphere. And we do this by first checking in a similar way as we did for bond paths for intersections between edges in the ring surface. So you can see how the ring surface is represented as this mesh. And we check for intersections between that mesh and the sphere itself. And we get a bunch of sporadically placed, disordered or unordered intersection points. So first we have to determine the ordering of these intersection points, which is rather simple. We find the point that's farthest from the midpoint of all the intersection points, call that point 1, and then point 2 gets to be whatever point is closest to point 1. We repeat that process and we can divine out an ordering of these points. Once the points are ordered, we can resample them so that their spacing between intersection points is much closer to the edge spacing on the sphere. And now our job is to make sure that each of these constraints, each of these constraint segments where the ring surface intersected the sphere, we need to make sure that that's actually represented in the sphere mesh itself. And this happens with a few steps. They're not super complicated. The first one is to simply move sphere nodes that are close enough to constraint nodes to the constraint nodes. So that part's simple. The next one is to split existing edges in the sphere mesh if those edges are close enough to constraint nodes. And so these two middle edges are to be split. So each of these gets split from one edge to two edge, simply adding the constraint node into the edge mesh. And then we update the triangulation around it to maintain a triangular mesh. We then check sphere nodes that are close enough to constraint segments and project those onto the constraint segments. And the last step is a bit more complicated. Now we actually check for intersections between constraint segments and existing edges. So we're essentially checking for a would-be intersection between two line segments in three-dimensional space. To make this simpler mathematically, we project these into a moving spherical polar coordinate system. That way we can just do a two-dimensional line segment intersection check. You do this for every constraint segment and every edge on the mesh, and you get a set of new nodes to be added to the mesh that come along with new edges. Then we follow this up with another round of jiggle mesh to relax the mesh based on all these new nodes and edges that we've added to it. And when we're done, we now have an updated spherical mesh that correctly corresponds to where the ring surface intersected the mesh in the first place. So this is a really simple example. A more complicated example is something that you might get in metals. So this is face-centered cubic copper that has lots and lots of ring surfaces. And you can see the ring surface intersections in the resulting triangulation here. So that's it for the sphere mesh generation. Now we can actually construct the gradient bundles themselves. And this amounts to seeding gradient paths at the nodes of the sphere mesh and along the edges of the sphere mesh. But there's a bit more bookkeeping that goes into this. So I'm going to show the construction of the gradient path, the gradient bundle that corresponds to this orange shaded element. And the first step is to seed gradient paths from the nodes and along the edges of the element. And we do this adaptively so that we can constrain the maximum gap in between the resulting gradient paths. And in doing so, we can guarantee that we're not deviating from the zero flux condition by using a linear approximation between these gradient paths. And this green path is actually the existing bond path and the existing bond ring path. And so you can see why it was important for us to recover this in the first place, because these end up being perfectly coincident with one gradient bundle or another. There's other gradient paths that we seed out. These purple ones are gradient paths that just freely flow through the gradient of charge density. And the orange gradient paths and surfaces are those that we have to add after the bond point is reached. That way we can correctly close off the part of the gradient bundle that coincides with what we call the interatomic surface. Then we can close off the rest of the gradient bundle, and we get this comically large but zero flex surface bounded region. And the next step in our algorithm is to then integrate properties inside of the gradient bundles. And so taking this upper tip of the gradient bundle to just be representative of some general gradient bundle, what we're going to do is we're going to decompose the gradient bundle into a number of tetrahedra, and then we can integrate those tetrahedra. So the first step is to use isosurfaces of charge density to essentially cut off the gradient path, or the gradient bundle at multiple points. When we do that, we're going to recover a set of intersections between the gradient paths that form the gradient bundle and the isosurfaces that we picked in order to partition it. If we triangulate the polygon that's formed from these intersection points, then we can map that triangulation through as we partition down the gradient bundle by row isosurfaces. And this gives us a number of trigonal prisms. Each trigonal prism can then be decomposed into a number of tetrahedra. And the tetrahedra can then be integrated using Gauss quadrature tetrahedral integration rules. And so this ends up being incredibly accurate and also very fast. The last step is to identify special gradient bundles, things such as bond bundles. And to do this, we do a very simple algorithm using the sphere mesh that we use to construct the gradient bundles in the first place. You start from some element on the mesh, and then you simply move in whatever direction increases the value of the charge density in the gradient bundle that corresponds to each of these elements. When you do so, you partition the entire sphere into a set of non-overlapping basins that correspond to the maximum and minimum critical points on the sphere. And then if you seed out gradient paths along the boundaries of these basins, then you can recover the bounding surfaces of the special gradient bundles. And it's just that easy. And so once you've done all this, you can finally construct a differential gradient bundle condensed charge density for a real system. So let's see what this looks like using, again, ethyl alcohol as our example. So we're going to do a gradient bundle decomposition using about 5,000 gradient bundles per atom. And inside of each of these gradient bundles, we're going to integrate properties of interest, things like volume, energy, charge. And we're going to write down the value of the integral for each gradient bundle back onto the sphere at the point where each gradient bundle passes through that sphere. And in doing so, we get the differential gradient bundle condensed charge density. We denote the condensed charge density as big P, big calligraphic P, and P is a smooth two-dimensional function that you can map onto a sphere around a nuclear critical point to get what we call the atomic chart for that atom. And if you take the atomic chart for an entire molecule, then we call this a molecular atlas. Now the value of P at some point, so Pi at theta phi, is the amount of charge contained in the differential gradient bundle that's coming out of atom I at the angular coordinate, at the spherical polar coordinates theta phi, about that atom. And P has units of electrons per square radian because we're in this spherical polar coordinate system. You can likewise condense other volumetric properties. So for example, you can construct the condensed volume by just looking at the volume of differential gradient bundles. Or you can integrate the kinetic energy density inside of a gradient bundle in order to get the condensed kinetic energy. But let's look at the topology of the condensed charge density. The first thing we notice is that it experiences a maximum where a bond path intersects the sphere. So at bottom right, you can see where the bond path goes to the sphere, we've got a maximum value in P that corresponds to this carbon double bond path. We have another maximum that corresponds to the carbon-oxygen bond path, and the third maximum that corresponds to the carbon-hydrogen bond path. Now, in a presentation like this, I can use fancy animations to make all of this very spatially clear, but when you're constructing images for a paper, what we often do is use a stereographic projection to essentially unwrap the sphere into a two-dimensional image. So here's a stereographic projection that's centered at the carbon-carbon bond path. But fortunately, I am in a presentation, so I can use fancy animations for almost everything. And the fact that we have a closed function because it's wrapped around the sphere means that we can partition the condensed density into a set of non-overlapping basins, each with a maximum as its focus. And we do that, again, by simply picking a point and then walking uphill or in the positive direction, and we're guaranteed to terminate at one maximum or another. If we do this for every point on the sphere, then we end up partitioning the sphere this way. And if we seed gradient paths along the boundaries of these maximum basins, then we obtain what we call a bond wedge. So this is the image in the charge density of a maximum basin in P. if we do the same thing for the oxygen atom, then we can recover the corresponding bond wedge for this carbon-oxygen interaction. In doing so, we form the bond bundle, which is the union of bond wedges with some shared area on their boundary. And you'll also notice with oxygen that we have these orange and yellow shaded regions that don't have a bond path going through the maxima. So these are lone pair regions that we can observe directly from the condensed charge density. And we can likewise see gradient paths between their boundary in order to obtain the corresponding lone pair wedges. And so you can divide up an entire system into a set of bond bundles. And we've shown previously that bond bundles are useful. Just at a glance, you notice bond bundles have different shapes. So the red carbon-oxygen bond bundle is closed off, whereas the carbon-carbon double bond bundle is open above and below the molecular plane. And we've shown previously that this has to do with with how prone a bond is to electrophilic attack. We've also shown previously that when you count up the number of valence electrons in a bond bundle, you recover the bond order as predicted by the Lewis model. And importantly, the bond bundles that we recover as defined through the condensed charge density are identical to those that we recover directly from the topology of the charge density itself. And so that's cool. It's nice to know that using this, we can recover the Lewis model, because one thing that a new theory has to do is reproduce the results of existing theories. But let's look at something that no one's ever seen before. Let's look at a local energy distribution inside of a metal and see what information we can glean from that. Specifically, we're going to see a way to rationalize the preferred crystal packing of pure metals. So as my example, I'm going to use face-centered cubic copper. And if you do a gradient mineral decomposition in a closed system, then it looks a little bit different as these volumes evolve. So now every gradient bundle is going to terminate in one cage critical point or another. And in doing so, we recover the Wigner site cell for this material. Whereas in the open molecule case, we were terminating gradient bundles at some arbitrary value of charge density. Now all the gradient bundles terminate in a cage critical point. And when we do this for copper, we notice that we get a very different topology of the condensed density from what we were used to in organic systems. So significantly, the bond paths no longer intersect the sphere at maximum values in the condensed charge density. For some contrast, copper is a face-centered cubic material. Let's also look at a body-centered cubic material, niobium. So here the topology is the inverse of what it is in copper. When I say that, I mean that everywhere copper has a maximum, niobium has a minimum. And everywhere that copper has a minimum, niobium has a maximum value. And so they're essentially opposite in character. And this is the last time we're going to look at the condensed density for these metals, because what we're much more interested in is the energy distribution itself. And so
Hey,
at
Tim.
the bottom,
Can I interrupt for a second?
sure.
Just to understand, I had this question during reading the thesis also. This difference of minima and maxima inversing in copper versus niobium, is that because they have a different crystallographic geometry? So it is the implication of being arranged in a different crystal structure, or is it inherent to the element?
I'll get to this shortly, but it's inherent to the element. And in order to test that, one of the things that we did was we forced copper into the BCC crystal structure, and we also forced niobium into the FCC crystal structure. And the topologies of the condensed density and also the condensed kinetic energy, they do not change. You get maxima and minima in the same places.
Got it. Okay. Go ahead.
It's not just a consequence of the crystal structure, but importantly, the condensed density and the condensed kinetic energy, oops, wrong font here. Those should be fancy calligraphic characters. But the topology of the condensed density and the condensed kinetic energy go as one another. So everywhere that you have a maximum or a minimum in one, you'll generally find a maximum or a minimum in the other. And the energy distribution is much more interesting to us. And thanks to the virial theorem, when you have a system at equilibrium, just by knowing the kinetic energy, you also know the total energy. And so regions that have a higher value of condensed kinetic energy are the regions, or I'm sorry, regions that correspond to a higher value of condensed kinetic energy are the regions of lower total energy. And these are the regions that are stabilizing the system. And so in doing this, we're directly inspecting the intra-atomic total energy distribution in these systems. And this allows us to compare and contrast the stabilizing regions back in the three-dimensional charge density for these two systems. So let's see what that looks like. So on the left and the right now, we have the gradient bundles that correspond to the stabilizing regions in niobium and in copper. In niobium, we call these shapes spatulas and bats. You can see which one is which. And in copper, we call these shapes claws. And what's much more interesting is that these shapes correspond with the type of atomic orbital overlap that we would expect to see in these systems. So specifically, the bats in niobium seem very much to correspond to sigma bonding interactions between dz squared orbitals on the niobium. Whereas the spatulas in niobium seem to correspond with pi bonding interactions between, for example, the dxy orbitals. In copper, however, it's a very different picture. Now, the claws seem to correspond with delta antibonding interactions, corresponding to dxy orbital interactions. But this shouldn't come as any surprise, because we know that niobium has a half-filled D shell, and so it's only populating bonding molecular orbitals and bonding interactions. And so, of course, it's these bonding interactions that stabilize niobium. Copper, on the other hand, has a full D shell, and so it's stabilized by these anti-bonding interactions. And so this is something that's intrinsic to the element based on its D shell population. And so the crystal structure, the BCC or the FCC crystal structure, this is the crystal structure that allows these stabilizing regions to maximize the amount of stabilization that they provide to the system. Because these are the highest energy molecular orbitals, the highest energy interactions. By lowering their energy, you're stabilizing the entire system. And so that's something no one's ever seen before. And we couldn't have done that if we didn't have years of blood, sweat, and tears ruining all of my keyboards as I developed this algorithm. Let's look at something else that no one's seen before. Let's look at a dynamic energy distribution while a bond is formed. And since I'm getting a chemistry PhD, I should probably include a chemical system and not just metallic systems. So let's look at a Lewis acid-base reaction, borane plus ammonia to give us ammonia-borane or borazane. And so at a basic level, we can inspect the reactants and the products. And so we have ammonia with a lone pair wedge pointing down off of the nitrogen atom. And then we have borane that does not have a lone pair wedge. It just has 3 boron hydrogen bond bundles. These are stereographic projections of the nitrogen and boron atoms respectively. And then when we bring them from essentially infinite separation to their equilibrium bonding distance of around 1.65 angstroms, then we see that there's in fact a bond bundle formed between them. But we're interested in the dynamics of this. And so we can look at this step by step. And note that at 3 angstroms, even though there's a bond path and a bond point in red between the boron and nitrogen atoms, there is no bond wedge on boron to complement the lone pair wedge coming off of the nitrogen. So at this point, we would say that there's no bond between these two atoms. As we bring the 2 molecules together, at around 2.7 angstroms of internuclear separation, we do form a complementary bond wedge on boron. And so at this point, we'd say that a bond has formed. And then we can bring them closer together, allow them to relax to the equilibrium separation, and we can see the surfaces relax accordingly. And since we're doing this computationally, we're free to just play around with things. So we can also push these molecules past their equilibrium distance and watch the surfaces stress in response, and then relax as we bring them back apart. But the interesting part of this is that we can observe the energy distribution dynamically at each step in this process. So here we're looking at stereographic projections of the condensed density, volume, and kinetic energy on the boron atom. And these stereographic projections are centered at the boron-nitrogen bond path. And so at 3 angstroms, each of these stereographic projections has a minimum right where the bond path goes through the sphere mesh that would be around the boron atom. Right at 2.7 angstroms, when the bond wedge forms, the reason that bond wedge is there is because we now have a maximum that is formed in the condensed charge density. And we simultaneously form a maximum also in the condensed volume and the condensed kinetic energy. And then you can see as you approach the equilibrium distance, there's further evolution of these condensed properties. And one thing that we've noticed is that the condensed volume tends to control the rest of the condensed properties. And the condensed volume indicates regions of charge density expansion and polarization, which is another point of contact with chemical theory, where we think about different types of bonding as in regards to their extent of polarization or expansion of the charge density. And so these are things, they're not necessarily the most useful problems. These are mostly just proof of concept toy problems to show types of analysis that you need a gradient bundle decomposition algorithm in order to perform. And so I likely haven't shown you anything that you didn't already know. Of course, metals are going to be in the crystal structure that lowers their energy, but we were able to get at that in a way that no one has ever done before. And we were able to do that thanks to my novel software. And so I'm going to wrap things up now. So as the bulk of my PhD work, I developed the gradient bundle decomposition algorithm. What we have now is a proof of concept algorithm that serves as a general solution for any chemical system that we can throw at it. And it's taken about 10 years of effort, including 5 for me as a grad student and 2 as an undergrad before I joined the group as a grad student. These are novel algorithms for ring surface identification and the entirety of the gradient bundle decomposition algorithm. When you perform this on a system, you obtain the gradient bundle condensed charge density. This is an infinitesimal partitioning of charge density into regions of well-defined energy. And this is at the maximum resolution allowed by quantum mechanics. So with things like uncertainty in play. The condensed charge density allows for the direct inspection of local phenomena by giving you the ability to directly inspect the local energy distribution in a system. It leads to a natural redefinition of the chemical bonding region we call the bond bundle. And a bond bundle can be thought of a non-nuclear region of charge density concentration such that the local and system energy is lowered. So that's probably what you think about, what you think a bond is already. And when we look at bond bundles in organic systems, then we reproduce the results of the Lewis model. Bond bundles also indicate local regions of charge density polarization and expansion. Now, I showed some novel results from example applications that weren't themselves super useful, but we saw that in metals, the BCC and FCC crystal packing is the packing that maximizes stabilization from the stabilizing regions in those systems. And we also saw that we can observe the dynamic evolution of the local energy distribution while you're going through some change. And my algorithm would be useless if it was only used for those 2 toy problems, but now that we have it, we're using it for all kinds of research. So Malvika in our group is investigating grain boundary embrittlement. And she's doing so. So at the right, we have a sigma 5 iron grain boundary, and she's sticking boron or phosphorus in these void sites, and then seeing how this affects the stabilizing regions of the system and in what direction the energy goes. And so she's seeing how the embrittling agent affects things, how the placement of the agent affects things like concentration. And she's doing all of this by directly inspecting the local energy distribution in these systems. We have a collaboration with the Alexandrova group at UCLA and with Professor Amanda Morgenstern, one of our former group members at University of Colorado, Colorado Springs, investigating how we can perform artificial enzyme design. And specifically, we're trying to understand and predict the effects of electrostatic preorganization in these biological systems. And this figure that I'm showing here is what we call a condensed density, condensed difference density. So these are stereographic projections on this oxygen atom. And we've taken the difference between the condensed density in the neutral system with the condensed density in a system that has a plus or minus 10 megavolt, I think, per centimeter external electric field. And we're able to see these subtle differences. Specifically in this case, we're seeing that there's a redistribution of charge from a ring, from the ring region. So the oxygen has these two rings next to it. We're seeing a redistribution of charge between the ring region and the cage region as a result of the direction and magnitude of this external electric field. And again, we're getting at this by looking at local energy distributions and local charge distributions. Jordan Goss in our group is investigating Jahn-Teller distortions of metal-centered clusters. And so she's seeing if there's an indicator in the total charge density that will tell you how the energy and how the density will redistribute when it undergoes a Jahn-Teller distortion, and to see if you can predict the direction of the distortion. And we're also looking, Samuel Riddle in our group is looking at local elastic constants in other pure metals. And so here we've got rhodium that's undergoing a 5% compression or 5% expansion. And he's seeing how this affects the stabilizing regions of the system and how it affects the energy redistribution inside the rhodium atom. And then on the algorithm side, my future work includes re-implementing this as an open source library to decrease as much as possible the barrier to entry for other researchers to utilize this method. And then there's a whole hit list of improvements to the algorithm to just make it work with more types of software, get higher accuracy, speed things up, and introduce additional types of analysis. And I'll be continuing with this as a postdoctoral researcher. So that concludes my talk. I'd like to thank from the bottom of my heart everyone in the molecular theory group, Dr. Scott Imlay and Craig Mackey at TechPlot Incorporated. Craig's no longer with TechPlot. My thesis committee for being there with me through the whole thing. Office of Naval Research for funding us over the last 6 or 8 or 10 years or however long it's been that you've been sharing with us the faith that local energy distributions will give us new insight for materials design. And also, of course, the CSM chemistry department that gave me a POT fellowship my first year so that I could concentrate on research, and a number of teaching assistantships to keep me afloat. And with that, I'd like to take any questions you might have. Yay.